we have an example which we have been asked to find the equation of osculating circle of the curve, which is defined by y in the point x equal to 1. So for find the osculating circle, we have to know what is the osculating circle. Osculating circle is a circle which has a radius, and this radius has opposite with the curvature of the function. Suppose that we have this curve. If I get y is equal to 2x2 minus 4x plus 5, and if I put equal to 0, the delta is equal to negative. It means that y always be positive as a is positive. So y always is positive, and I suppose that is this axis, and the function will be something like this, which is passed from the point 5. So if we want to find in the point 1, and the y also will be equal to 3, and the osculating circle is in order we know what is the osculating circle, we have to know what is the curvature, because the curvature here is defined if we suppose that a smooth curve has a C, which is in the space given by R S. S is parameterized arc length. So the curvature kappa at the point S is equal to derivative of tangent vector over S over the arc length, which is parameterized. Let's come to this example, and I want to tell you what is the concept of curvature in here. If we get this as a y-axis and this x-axis, if you move toward this function which parameterize over this arc length, for example as S in terms of t, in every point has a specific curvature. What is the curvature? It means if you move with the wheel here, that is it is the osculating circle in every point, how much sharply the curve turns, you will turn. So in every point we have a circle which is defined the tangent vector over this, and this has a radius as r, and in every point this tangent will change. And how much this tangent change over the arc length of this curve, it means the curvature, and it will be has a different, it means in here is very sharply, so the radius will be increased, but here will be a greater radius, but whatever is here will be sharply, we have to change, so the radius of this osculating circle will be smaller. So we have to find the curvature. So the curvature here, as it is defined, is not useful to find the curvature in terms of the function which we have as fx equal to 2x2 minus 4x plus 5, and the s which is defined by x and 2x to minus 4x plus 5. It is parameterized in the term of arc length of this curve, and kappa has to be defined in terms of this function, because it is not useful here and we cannot know how we can calculate the tangent vector over this will be t, which is derivative of this curve s ds over dt, which is normalized if we unit, so we can divide by the norm or magnitude of ds over dt. So this is a tangent vector in the point P, and how much this change over the S as the arc length of this curve, it means the curvature. So curvature, according to the definition, kappa, excuse me, okay, and the kappa will be equal to the norm of dt derivative of tangent vector over s as the arc length of the curve. So if I go and open this one, we cannot get t over s, but in every point will be in term of t, and s also in term of t. So I can get derivative of t over dt is divided by derivative of s over dt, because it is a parameterization, because s is in term of the function, and here s is equal to x, which is in any point will be changed, x in term of t, xt, and yt, which is equal to 2x to minus 4x plus 5 in term of t, and it is the parameterization. So I can get for any in term of this dt over ds over dt, this is a spring, I can write as a spring, norm of a spring, and here dt over dt, which I have to get derivative of this. So I want to go further, and if I suppose this one, and the curvature and the norm is we have the opposite relation with the r, which is radius of this osculating circle. So if we want the curvature, then by inverse of curvature we can find the radius. So radius can find, which is related to curvature. So we want to know what is the curvature. And then also we can go to the center of this circle, which is x0 and y0, and we want to find this one in order to reach the equation for the circle. So it is 1 over norm of kappa 2. So here we can find first the curvature. The curvature, if I want based on this y or is equal to fx, so it's better I get the formula, which is easier to find, derivative of t over t and a spring, because we have to find this in terms of s, so we have to change. As we know, t is equal to this one, ds over dt over e, because we have right here before, so ds over dt over the norm of ds over dt. It means that a spring over norm of a spring. So a spring is equal to t multiplying the norm of a spring. I want to get the derivative of t here because I need according to the formula here. So I need t prime. So I get derivative of a spring here, then we can find what is the t prime. So I get derivative of a spring, so is equal to derivative of t is t prime times a spring plus derivative of a spring, which is second derivative multiplying t. Now if I get cross product of a spring in S second prime product in second derivative is equal to t times a spring in t prime a spring plus, and if I multiply by product, so we will get t prime, and this is a scalar. If I multiply, I will power 2 plus t, and this is also spring a second. It will be equal to norm of t times norm of t prime in sign between t and t prime, multiply in a spring norm 2 plus here also is norm of t in the norm of t in this sign between t and t, multiply norm of a spring and norm of a second. If you see here, t and t prime are perpendicular to each other, so it is 19 degree is equal to 1. And this is the angle between t and t is 0, so this will be 0 and deleted. So this one is equal to spring product by a second is equal to norm of t as it is, the unit vector is equal to 1 multiply in t prime norm of t prime multiply in a spring norm power 2. So now I could find what is the t prime. So norm of t prime will be equal to, so here we have this formula. I suppose that I put this 2, and here before we find this one is equal to 1. Now with 1 and 2 I can rewrite again the curvature to reach the formula for curvature. So the curvature will be equal to, it was according to 1 and 2, it was the norm of dt over norm of a spring. Now I can rewrite this because it is t prime, so I can write a spring product by a second over norm of a spring power 2 over norm of a spring, because this is t prime and the norm of t prime equal to a spring product scalar by a second over a spring 2. So now I can bring a spring in denominator, so we will reach to this formula. Now it is very important formula for curvature. According this, which we could find the curvature or kappa in terms of S, which is defined by fx equal to that function. So we can get just this and very easy to find the curvature. So here we get this formula kappa is equal to this in terms of the parameterized arc length of S for the function f. But here this formula as has written in this theory. First, it was if C be a smooth curve given by S, then the curvature couple of C at point T is given by couple is equal to how much change T respect to S. It means the norm of the prime over S prime. And also if C is three-dimensional curve, as we can use this curvature which I proved before, and this one is the direct consequence of couple because when we have the y is equal to fx, we could able to write here y is equal to fx and the kappa, so s is equal to x and fx or x and y. So s prime will be equal to 1 and y prime, and s second will be equal to derivative of 1 is 0 and derivative of y prime is y second. And then kappa is equal to cross product of the prime in S second. So we have the cross product of this one, the norm of this over norm of S prime. Norm of S prime will be radical 1 power 2 plus y prime power 2 2 fourth, 2 third power. So here the norm of this square, this cross product will be 1 multiplying y sec 1 minus 0 multiplying y. So we will get norm of y sec 1 over this norm, which is exactly this formula which has mentioned as 3.7. Let's we go to continue our example. Let's continue with the what is S. S according to the formula was x and 2x2 minus 4x plus 5. So I can find the derivative of S, which is equal to 1 and 4x minus 4, and again derivative of S prime, which is equal to 0 and 4. And now we find S prime product by S prime derivative, which is equal to 1 times 4 minus 0 times product of this, and we will get 4 over the magnitude of S prime power 3, and S prime is equal to 1 and 4x minus 4, and so I can write here norm of S prime will be equal to radical 1 plus 4x minus 4 power 2. And now we put in the curvature, and according to this formula it will be equal to 4 over this radical power 3. Now if I want to find the radius in the point 1, and I need to find the curvature in the point x equal to 1, which will be 4 over, this will be 0, and we will get 1. So the curvature in the point 1 will be equal to 4, and then radius of osculating circle will be equal to 1 over 4. So if we go back to this, here we could find the r, and just we want to find x0 and y0. Let I write the circle equation. Equation of a circle is equal to x minus x0 power 2 plus y minus y0 power 2 is equal to r2, which is 1 over 4 and power 2, which is 1 over 60. Now in order to find x0 and y0 that which the circle satisfied, and passing from the point P, it is 1 and 3, so I can put 1 and 3 in this equation. So I will get 1 minus this equation, 3 minus y0, 2 is equal to 1 over 60. Now I want to find x0 and y0. If I get to this function I had before, that the function is this, and the point P is here, and the osculating circle is here, and the radius is this one, and the y is the function is equal to 2x2 minus 4x mod plus 5. If I get in which point this derivative is equal to 0, I can find this t, it means the slope of this in the point P. For the slope of this function, I want to know y prime, which is equal to 4x minus 4, and if I solve this equation, I will get x equal to 1. It means that the slope over the curve and also the osculating circle is parallel with the x-axis, and is equal to 0. So because the m is equal to, slope is equal to the tangent of pi over 2, which is equal to 0. And now we want to we can get that the point of the circle has the same x equal to 1. So we have the 1, but we don't know what is the y, and we are going to find what is y0 for this center. In order to find y0, we can put in the equation x equal to 1, then y0 also will be found. Let's I put here y prime x1 minus 1 power 2, 3 minus y0 is equal to 1 over 16. So 3 minus y0 is equal to 1 over 4 or minus 1 over 4. If I suppose I will get two answers, y0 is equal to 3 minus 1 over 4, and also another answer 3 plus 1 over 4. And the first one will be equal to 11 over 4, and the second is equal to 13 over 4. And which one is acceptable? Actually, if we go as the center is above the point P, so the point P has the coordinates of 1 and 3. So P has have 1 and 3. So the answer of 11 over 4 less than 3, and it's not acceptable. So the right answer will be 13 over 4. And then we can write the coordinates, the equation of the osculating circle, which will be equal to um, x minus 1 power 2 plus y minus 11 over 4 power 2 equal to R2, and R2 is equal to 1 over 16. Thank you for your attention. Hope this video also be useful for you. I will appreciate if you subscribe to my channel. Be always blessed.